Welcome, everyone. Today we are going to talk about safety. Safety is an important aspect, especially in the latest times when some people, some governments state that C++ is not a safety language. Uh, this way, I would like to show you some examples where actually C++ can achieve more than any other language in the world. And actually, on the example of the Quantities and Units library, we will see how we can improve the safety, not only of our software, but also of our daily lives, because we are not only programmers, but also users of our products often, and that we are going to talk about soon, right? So, not that long ago, self-driving cars were the thing from the sci-fi movies placed in a distant future, right? If you've seen some old films with, I don't know, Arnold Schwarzenegger or other guys, it was like years 222,000 or whatever, and the guy was getting into the car, and the car was autonomously driving to the destination without a driver. This distant future actually starts to happen right now on our roads. This is our reality right now, right? And while the autonomous cars are driving us to the destination, we would like to be able to rest, maybe sleep, or do our work in the meantime, trusting the machine that is doing its job. And it's not only about autonomous cars, right? In our daily lives and in our current reality, we depend on machines more and more on daily basis, right? We have surgical robots, we have planes, we have rockets, we have plenty of other things that make our life easier, but also may make them unsafe if they are not programmed properly. And there will be more and more things that we will depend on in the near future. C++ safety is a major concern in the C++ community in the recent years. We discussed potential improvements to the low-level fundamental types, like safe integer types, for example, and other possibilities to, for example, find overflows, detect truncation, and so on. We also would like to update some core language rules, for example, initialization, to be safer and better. But we can also provide safer high-level abstractions with libraries, and this talk is an example of one of such cases. C++ developers need some help here. It's not only about training, because we lack a lot of training in our industry in order to make our engineers grow, but also it turns out that the safety domain is a special domain in C++ programming, and not many people have experience in this. And this experience is quite hard to come by. And it also happens that often in this domain, people that use C++ are actually not C++ programmers, I mean not experts. Those are just physicists that do the work using C++ as a tool, right? So they are not template masters, they are not able to understand the template errors by C++ metaprogramming libraries. And that's why we have to try to somehow address this community as well. There are plenty of effective industries by such libraries. The obvious choices are the autonomous cars in aerospace, embedded industries. This is the first that comes to our minds, but there is much more. There is manufacturing, maritime, military, astronomy, GUI design, even audio. We had really nice talk about audio on CPPCon last year. Also finance, including even HFT. So plenty of different industries can benefit from such a library. It's not a niche, it's actually really popular and needed thing on the market. And this is not that well, first of all, this is really hard to use C++ in many cases, but units and quantities are not only about programming, they are inherently complex problem by themselves, right? Even in daily lives, not talking about programming at all, we often have problems with communicating about units. In the history of our basically history of humanity, we had plenty of different issues with communicating and using units. Let's start with Christopher Columbus, that on October 12, 1492, unintentionally discovered America while traveling to Japan and India, right? Actually, he survived because he made a few mistakes. He used different length for a mile that he was about to use for his calculations, and because of it, he thought that the world is much, much smaller. That's why when he reached Bahamas, he thought it's Japan already, or India. Vasa was a famous warship that in 1628 sank less than a mile into her maiden voyage. The result of this was the 30 sailors died, unfortunately, during this accident, and the reason for it was that one of the sides of the ship, of the hull, was thicker than the other one. Archaeologists claim that it is the reason because there were two different teams working on two different sides. One of them were using rulers that were calibrated in Swedish feet, which is 12 inches. And then the second team was using the other ones, using Amsterdam feet, that was 1 feet shorter, 1 inch shorter, yes. And because of it, it was heavy on one side, also because the center of buoyancy, because of other errors, was above the water. It was really easy to collapse during windy day. Air Canada Flight 143 on July 23, 1983, ran out of fuel at the altitude of 12,000 meters. The reason for this was that fuel had been calculated in pounds instead of kilograms, and there was not enough to reach the airport. Fortunately, no one died. The airplane glided to the nearest airport and was able to somehow land, and everyone survived. British rock band Black Sabbath, during its Born Again tour in 1983, ordered a replica of Stonehenge as props for the scene. Unfortunately, the manager, while submitting the order, wrote down the dimensions in meters when he meant feet. So as a result, they built huge replicas that were really expensive, and they couldn't fit in nearly any venue they were providing the concert. As they said, it cost a fortune to make, but there was not a building on Earth that could fit all of this into it. Actually, it was bigger than the real Stonehenges. Korean Air Cargo Flight 6316 on April 15, 1999, crashed due to miscommunication between the first officer and the pilot. The first officer misled 1,500 meters to 1,500 feet and ordered the pilot to go down. Pilot obeyed. Entire crew died, 3 persons, and 5 innocent people on the ground as well. Mars Climatometer is probably the most famous accident that we had in our engineering, right? In 1999, it failed to enter the Mars orbit and crashed while entering its atmosphere. The reason for it was that actually NASA was using SI units while the Lockheed Martin was using US customary system, and they didn't communicate well between the interfaces of different modules in the space probe. Clarence the tortoise, in February 2001, was moving from one zoo to another. The crew of the Moon Park College Zoo built an enclosure for it based on the information that they obtained through the phone from the source location, that this turtle weighed 250. It turns out that it was 250 kilograms, not pounds. As a result, Clarence broke entire enclosure in the first night, and they found him in the garden eating vegetables next day in the morning. Tokyo Disneyland Space Mountain coaster derailed in December 2003. The reason for this was a broken axle that was caused by some confusion after upgrading the specification from imperial to metric units. There is a bridge between Switzerland and Germany over the Rhine River. The bridge was started by 2 different teams on 2 different sides, and they were meant to meet in the middle of the river. Unfortunately, it turns out that the Switzerland and Germany are using different reference level for a mean sea level. Germany is using North Sea, while the Switzerland is using Mediterranean sea level. The difference is 27 centimeters. But if you think it was the difference, you are wrong. The difference actually was totally different, as we are going to learn later on. But basically, there was a sign error, and one of the teams, instead of subtracting the value, added the value because they forgot which one is lower. An American company sold a shipment of wild rice to a Japanese customer, quoting the price of 39 cents per pound, while the customer thought it's 39 cents per kilogram, and then they had to resolve the issues during the transaction. And even recently, in October 17, 2023, The Guardian provided an article stating Malawi swelters with temperatures nearly 68 Fahrenheit above average. If you know something about Fahrenheit, it's quite a lot above the average, right? The actual temperature increase was 32 Fahrenheit only, and the reason was because they misled the abstractions in affine space. So they used differences and points and recalculated the title that was meant to be published in Europe. Then they translated this to the US and used incorrect calculations to do that. And there's plenty of documented medical dose errors that happens all the time because medical dose errors and units are really, really strange and hard to communicate as well. And nothing of this had C++ as a source of the issue. C++ just adds another layer that makes this problem even harder. Let's see some typical production issues that we may find in our software. This is one of the open source softwares that I contributed for a while. And the Windows interface is really scary, and this actually motivated me to start working on physical units libraries. As you can find, double can be used everywhere, right? It's so hard to actually remember the number of arguments. It's so hard to refactor this function by changing the order of them or adding a new one in the middle. It's insanely hard to basically maintain this software. Another function provides plenty of magic numbers. I was afraid to touch it. I don't know what it does. No one does anymore. Such software uses plenty of conversion macros to do the conversion from one unit to another. Of course, not all of the conversions are defined, so you have to do this in steps, which is another inefficiency in the software. But it turns out that even with such an approach, there's a possibility to do mistakes. When I grabbed the same repository for the same macro, I found at least 4 different results in the same repository. This is one header file. Those functions are one next to each other. Exactly, this is copy-paste of the header file. We have distance, specified as latitude, longitude, double distance, latitude, longitude, latitude, longitude, longitude, latitude, longitude, latitude, to be consistent, right? Or to be consistently inconsistent, the same applies to distance and bearing, here and here. How to make it work correctly, how to play with the software, how to refactor stuff if the interfaces are like this. And you think this is just a bad open source software that doesn't have any standards in the rules. I'm doing this for 7 years. And when I started talking about this, plenty of people contacted me saying, I cannot share my source code, but my source code is much worse than the one you're presenting in your presentations. We have much bigger issues in the production as well. And I assume you are here because you know something about it already. That's why we want to improve. So I started to write the MP units library about 7 years ago, and also it is proposed for standardization. Standardization is not the ultimate goal of this library, but it would be nice to have it in the standard if only possible. First of all, of course, we want to provide compile time safety, right? By this, I mean correct handling of physical quantities, Unix, and numerical values, correct and detectable at compile time. Performance has to be as fast or even faster than working with fundamental types like double. Otherwise, no one in C++ industry will use it, right? There should be no runtime overhead and no space size overhead, which is for us may be obvious in C++ domain, but if you look for other solutions like in Pint or Java, they are paying enormous cost for abstractions on units, both in runtime performance and in space needed to store those abstractions. So C++ is an awesome language, probably the only language that allows providing all of the features of this library in the way we do here. Great user experience. As I said, typically our users are not engineers, C++ masters. They are just using this as a tool to make the things done. They do not understand complicated template error messages. We want to provide something as readable and as easy to use as possible. And also easy to use and flexible, because this has to be extended by the users for their own needs. Scope. We should be able to provide any unit's magnitude, huge, small, floating point, any of those. We should model system of quantities, system of units, the affine space abstractions, and we should provide, of course, text output for debugging and printing stuff. There are scalar, vector, and tensor quantities we would like to support, and also there are some users that would like to use this with natural units, which is quite tricky if you know the domain. And of course, it should be easy to extend. Currently, MP units compiles with C++20 on two major compilers, GCC and Clang. Apple Clang also somehow supports this because it's always like one release behind the Clang. MSVC unfortunately sucks and doesn't compile it at all. I tried to fix this, but there are just too many issues in the MSVC compiler only for C++20 support. I'm not talking about C++20 features here right now. Hopefully MSVC will catch soon the party, but for now, I have to deal with GCC and Clang. Besides C++20, we try to benefit from the latest possible extensions to the language in order to provide the best API possible for the possible standardization in the future. Right now, we consider C++29, so C++29 should not be fixed to C++20 because it will be already old at this time. We should try to benefit from the latest feature as much as possible to provide the best possible experience to our users. That's why we also benefit from stud format from 20, C++ module from 20, but also with additional 23 abstractions, and possibly we also use 26 abstractions if possible to improve the library. There are really nice features coming in 26 that could improve this library as well. But always we try to be compatible with 20. So all of the new features come with workarounds provided with compilation per processor macros to be able to work compatible with C++20. So don't worry, C++20 will be enough for this library for a longer time at least to compile it fine. Only if you have a better compiler, newer compiler, you could benefit from simplified interfaces or maybe a bit faster compile times. The library is available on GitHub, in Conan, and you can find it on Compiler Explorer as well. Talking about standardization, I provided this paper like 4 or 5 years ago. It was before COVID, so yeah, time flies. 5 years ago, at least, where I provided analysis of what is on the market and asked the committee if we want to follow this path. The answer was yes, and I started my work on standardization. Unfortunately, COVID happened in the meantime, so everything slowed down, but there are more papers coming. In 2980, I provided motivation, scope, and plan for physical units library, and in 3045, I'm describing the design and all of the aspects in detail. There are also some associated proposals, some dependencies for this library. We would like to have also the library of number concepts that would allow us to provide better interfaces, better constraints to our interfaces. I implemented a basic fixed string and provided a paper about it that will allow us to have standardized way of passing text to NTTP parameters of templates. And also we could benefit from compile time param numbers if this was standardized in the library as well. It seems that there's a high interest in both ACCU committee and in C++ community to have it standardized. The aspects are first of all safety, but also it's important to be standardized because this is about so-called vocabulary types. Vocabulary types are the types that are used to communicate between different vendors interfaces. And those are exactly the use cases here, right? Talking about Mars Climate Orbiter, NASA, and Lockheed Martin, they should have common language to communicate their interfaces. Otherwise, we'll have mistakes like this all the time. Before we go into the interfaces to C++ code, let's maybe talk about a bit about the domain itself. So let's do some simple introduction. We have system of quantities, and the system of quantities is a base for several system of units. This is something that this library does a bit differently than all of the others in the market because most of the libraries scope only on system of units, one or more of them, but none of them tries to model properly system of quantities as an orthogonal entity. But this is how it's defined officially. And system of quantities is a set of quantities together with a set of equations relating those quantities together. We have one big system of quantities that is specified, provided by ISO. It's a system of quantities based on the 7 base quantities that you are probably aware of. I will show them on the next screen. And there is system of units. System of units is a set of base units and derived units together with prefixes for a given system of quantities. So system of units is always based on system of quantities, and SI, provided by CGPM, is based on the ACCU, and they state it officially in their documentation. Those are the major entities involved in this domain. Dimension may be either a base dimension or a dimension of a derived quantity, and we have 7 base quantities in the ACCU. Length, mass, time, electric current, thermodynamic temperature, amount of substance, luminous intensity. Each of them has the unique symbol. We also may talk about dimensions of derived quantities. For example, force is denoted as LMT minus 2. But notice that the force by itself does not have an associated symbol. There's no such thing as a dimension of force. Force has some derived dimension based as being a product of base dimensions, but it's not a derived dimension by itself. It's not like a strong type, right? And this is what most of the libraries in the market do, let's say, incorrectly, because they define things like dimension of speed, but there's no such thing actually in theory and in the domain, because dimension of speed or force is just a product of base dimensions rather than a thing by itself. Dimension is not enough to describe a quantity, it turns out. There are a quantity of different dimensions, of course, like length, time, speed, power, but there are also quantities of the same dimension, but different kinds, like work versus torque, frequency versus activity, or even things like area versus fuel consumption, right? Fuel consumption is like liters per kilometers. Liters is a volume. If you divide volume by length, you get area. But I would not like to be able to add football field to the fuel consumption of my car, right? It would be insane to allow such calculations, at least in some domains, because maybe you have a domain where actually it doesn't matter. Also, there may be quantities of the same dimension and the same kind, but still distinct. Radius, width, height are different quantities. The same as potential energy, kinetic energy, thermodynamic energy. Sometimes you don't want to mix those in the interfaces, right? Official documentation states that there is something called quantity reference, and quantity reference can be a unit. This is a strange term, and especially in C++, it's quite overloaded. So I don't know if the term will survive, but we try to be, at least for now, compatible with official specs, and saying that quantity reference, being in this case a unit, is basically designated by conventionally assigned name and symbol. And you have base SA units for all ACCU dimensions, right? We have also some derived units, and derived units may be shared between different quantities, like heat capacity and entropy are using joule per Kelvin. But also it turns out that some quantities have dedicated units for their needs, even if they mean exactly the same. So 1 per second is a unit by itself in many domains. But if it's about frequency, then we should use hertz. If it's about activity of radionucleosides, it should be becquerel, even though it technically is 1 per second in both cases. And you should not be able to say activity is measured in hertz or frequency in becquerels, because it's incorrect. Additionally, quantity reference is a measurement procedure or a reference material, but this is something that we are not going to cover in C++. And quantity, by definition, is a just number and a reference. So those numbers may be either scalars, vectors, or tensors. This is also important in the aspect of linear library usage. We would like to address those use cases as well. And right now, no library on the market can survive that in the C++ industry. The only one that I'm aware of that survives it is pinned in Python, because it's based on NumPy. The basic operations we do in the library are, of course, simple numeric operations like division or multiplication by scalars. We can, of course, convert some units and find some common units during conversion. This is what Chrono does. But something new that comes with this library is dividing different quantities or multiplying different quantities by themselves, right? So you can get speed, and speed by time is length, and so on. We can also multiply the same quantity to get even another one, like area. We can divide two of them to get a dimensionless quantity, or we can do the inversion of a quantity to get another quantity, like in this case, frequency. So let's see how the code using quantity unit library looks like in practice. This is a code that is legacy one, with no library used, right? What's important here is that each and single identifier tracks the unit being used. If you're not using this right now, probably it's really hard to reason about the code you develop or maintain, right? We have distance in meters, speed in miles per hour. Then you have provide here some ratios in order to convert those. Actually, this is, I think, meters per hour in this case, and this is miles per hour. It's even hard to not find out those postfixes, what they mean. And you have some result. In order to get the result, you may provide magic numbers. But we don't like magic numbers. That's why in the library, we typically provide some conversion macros. This is something that you've seen already. If someone thinks that macros are wrong, then people provide consexp, nice conversion factors. Yes, I'm good, I'm using consexp. And this is where we have in many cases. With the units library, you don't have to spell any units in the names of the arguments or variables, because this is embedded into the type. In this case, we're using CTAD, so class temporal argument deduction, to not spell it, because it will always deduce the correct type used on the right-hand side in the initializer. I'm just interested in the abstraction here, and saying I'm dealing with a quantity here. It's always better than say auto. With quantity, you know what you're dealing with. With auto, sometimes you may be confused, right? But CTAD is enough to spell it. You don't have to spell entire type. And you're using here meters, miles per hour, and you can easily divide it, take the value in seconds, and have the result without a need for an intermediate value like here. And you get exactly the same result in both cases. Right? There's no need to track units. And library by itself knows all the conversion factors, so you don't have to provide any magic numbers, macros, consexp, ratios. And the intermediate results are not needed because the library will do all of those steps for you if needed. The main goal of such a library is to generate errors. If you are not going to make any errors in our software, this library is not needed. Right? If you are flawless, then why to bother? Just use doubles. Right? So if I will provide a mistake in my calculation, instead of division, I will do multiplication in both cases. This code will happily provide the result, whatever it means. If you will do this with library that is safe, you will get a compiler error like this one. No magic member function to call to foo. Constraints are not satisfied with the unit being second, because unit of second is not the unit of quantity of length to power of 2 per time. All right? You can also provide functions with those interfaces, right? If you don't have library, you have to specify arguments using the same syntax with postfix, but also functions should get the postfix to say what is the result of it. So this is time to goal in seconds. And then you implement the logic of a function. With strong types, you know exactly what is the unit in the type. So you don't have to encode this in the variable name. With cplusplus20, we can have this great syntax using NTTPs where it is really easy to read and reason about. And this was not possible before cplusplus20. That's why this library requires at least cplusplus20 to work. And there's no way to provide it earlier with those interfaces. At least it would be really, really, really hard. So if you want to call this function, you have to, again, provide all of the variables with the postfixes, and you will have some result. In this case, you don't have to do postfixes. I just provided those because I want intentionally to have two different objects here. I will show you why in a moment. And this is how I create entities, right? 10 kilometers per hour. And I call it, and I get exactly the same result in both cases. If I will use kilometers here, this code will happily compile and provide some result. Of course, it's incorrect because this is not meters. Translation was not applied. Conversion, right? In this case, of course, if only it is non-truncated conversion, then the conversion will happen automatically by the library, and you still have 400 seconds, the same as it was before, because this is the same value, just converted to a different unit. If you will provide the arguments in a different order, in both cases, you will get another incorrect result from the legacy code. Here we'll get another error, right? Stating could not convert speed from quantity of kilometer per hour to meter. If you do another error with multiplication in the implementation, you will get yet another issue from this code. And here we get another compile error saying that we cannot convert the result being kilometer per hour to second. And what about performance? If you have left code and right code, this is the assembly of the left code. This is the assembly of the right code. Exactly the same instructions. In this case, they are reordered because I'm doing the computations in another order, but those are exactly the same instructions. But this often requires us to convert the input and output to some specific unit, and then from some specific unit to maybe unit you are working with. With strong types, we can provide better abstractions. We can provide generic interfaces. We may say that we have quantity of length, quantity of speed, and quantity of time being used here, but we don't spell what is exactly being used, what unit is being used, what representation type is being used, we don't need to pay for those conversions if they are not needed. It would not be possible if you could not constrain this easily with concepts, right? If it was interfaced just on doubles, there would be no way to spell it for this to be type safe. If there were no concepts, it would be really hard to make it right. Arguments you could constrain maybe with enable if in an older language version, but constraining the return type, it's quite problematic with enable if. So let's see. I may provide fits and miles per hour as arguments and get the result, convert this to seconds, and find out how much time is needed before I have to turn right on the crossroad. I can use different units using distance to the Garda Lake from my home, the average speed I predict to have, and find out what's the time in hours, in this case, to destination. The only cost we pay is the cost of this division. We don't have to pay for any intermediate conversions on the input and output, because typically the user provides something in kilometers and hours, would like to have a result in hours as well. So forcing the user to convert it to meters per second, meters, and then seconds, and then back, it's just paying for unneeded calculations and also possibility to do truncation errors and some precision errors, right? If I want to run a half marathon distance, I can provide the distance kilometers, pace in meters, seconds per kilometer, and provide it the same function. And what I will get? A compile time error, right? Because pace is not a speed. But we often forget about it, at least non-experts forget about it while we're working with the watches, that pace is not a speed. I always have to explain to my mom or a girlfriend what does it mean to have a pace of this speed, of this value. Right? And you get information that quantity of seconds per kilometer is not speed. If you do it correctly, provide inversion of pace, then of course you can find out that the expected time for the race is 1 hour, 38 and 27 seconds. By the way, notice how easy it is to cooperate with this library with std.chrono, right? It just converts implicitly to chronotype, and you can print it with chrono helpers. Also, if you're using affine points abstractions with quantity points, you can have 2 points with cloud base, glider altitude, have a thermal strength of 4.5 meters per second. This is how fast you are going under the cloud up. And find out, by subtracting those two, find out how much time is left before the cloud will suck you in. So you have to exit this before. Those are just only some examples of how working with such API works. But let's scope on safety features in isolation, what such a library provides. First of all, we have safe unique conversions, right? We provide some quantity, and we can convert this to a quantity in a different unit and get the result. You can convert this either with a member function or with a converting constructor. Magnitudes of the source and destination are known at compile time and applied by the library automatically, so you don't have to worry about the conversion factors. Right? The library uses that information to calculate the result for you automatically. We cannot use std.chrono, we cannot use std ratio that is being used in std.chrono duration because it has some limitations. It's not enough for a general purpose library for physical units. Std ratio is implemented in terms of std.int max, which is huge, but not big enough. Impossible to define units with huge or tiny magnitudes like electron volt, Dalton, and many others. Actually, std ratio is not able to cover 6 SI prefixes that are specified in the standard, but none of the libraries, none of the compilers will ever support them. Because int max t actually is not the size of the biggest integer on your platform. It is int64, and it will never change. You know why? The answer is ABI. So even if it will get longer integer types, int max t will not change. It sucks. So std ratio will never cover those prefixes that are specified in the standard, 6 of them as of today. Besides having huge and tiny ratios, also we sometimes need to have an irrational number being a ratio between two different units, like radians and degrees. You cannot express this with std ratio at all, right? So how we defined units? We've provided our own abstractions, like Mach power to specify prefixes. It's a power for kilo. So we provide kilo as a class template and then variable template that is useful to build things on the fly. And we provide meter, we provide second, and we provide unit symbols in a specified namespace, dedicated namespace for this, just using kilo meter. Unit symbols are provided in an isolated namespace, and they are opt-in because those short symbols easily collide with existing symbols in your library. We don't want to trash your namespace, your scopes, with all of those short names. So you have to opt in order to get them. You can use either using directive or using declaration, whichever suits you better. Also, not everything is just a prefix of another unit. Sometimes you have to have conversion factor different than the prefixes. So you specify hour, minute as being 60 seconds, or hour being 60 minutes with this syntax. Or sometimes you have to use ratio as a factor, like yard is that ratio of meter, and then have also mile here. So this is how we deal with different ratios in the library. Another feature of the library is preventing truncation of data. I see you laughing here, but you know how many times I already ended up with 0 in the libraries like this? Because I was just dividing things on integer types. This would be pretty surprising on the highway, right? To see such a sign and all of the cars stopped. So in case we are using integral types, then there's possibility to do truncation. If you will have meters and you would like to convert this to kilometers, of course it truncates. The result will be 0, and all of the cars will have to stop. That's why we have a compile time error, both using this member function and both using the conversion constructor. Floating point types are considered, at least for now, value preserving. We here follow what std chrono duration proposed, as we don't have any better ways to state what is value preserving and what is not. We follow std chrono duration abstractions. Hopefully, we'll be able to improve. There are some type traits proposed in the pipeline that may make this even better. But for now, we assume that floating point is value preserving. We know it's not, but we assume that. And in this case, we can convert meters to kilometers with function or with conversion constructor, and it compiles. We can also use here integral type and explicitly cast it with value cast to specific type before we convert, and then it works nice. Here also it works because the double is used by default. Here we use int, right? Here is the double by default in the quantity, so it converts as well. You can also force the conversion explicitly from the code. If you have ints, you can do force in kilometers. I know it reads long. I know it reads wrong here because in the subject of quantity library, reading force in kilometers seems wrong. If you have a better name to propose, please let us know. We thought for a few how to express forced conversion to not specified force in newtons. In this case, it is overloaded term. But for now, we're using force in, and we're looking for a better name. Or you can use value cast here in kilometers of Q1. Also, conversion from a floating point representation to an integer representation is considered truncating, right? So you can use value cast as well, but this time not with unit, but with a type, saying I want to force this conversion from float to int, and then it compiles. All right, but I think all of those things were quite obvious to you, right? Because you know probably pseudochroma duration, so this was not a surprise. But let's see how those things already work in practice. Let's find out why Columbus thought that he reached India. Right? He started from Europe, went to Canaries, and then from Canaries he reached Bahamas. How it happened that he thought he is in India, and that's how actually he did not die on the ocean. At the times, there was a famous cartographer called Abu al-Abbas Ahmad ibn Muhammad ibn Kathir al-Farghani, aka Afraganus. And this cartographer was from Persia. Columbus learned from him that the estimated degree of latitude basically spans 25.67 miles, right? So he thought, okay, so latitude on the equator, longitude should be roughly equivalent. So this is how far 1 degree on the Earth takes to travel. 56.67 miles. The length system used in Europe at this time was the Roman system. The Roman system was based on a Roman foot. The length of the foot officially right now is measured as the length of this foot on the statue of Quantities. This is, if you don't see, it is 296 millimeters. This is official source for the truth of Roman mile, of Roman foot, sorry, in this case. Roman pace is the length of every other step of a Roman legionary. It was equal to 5 Roman feet. Roman mile was the total distance of the left foot of a Roman legionaries hitting the ground 1,000 times. Easy system to implement, right? Based on the actual realities of the era. So we have an estimated degree, 56.67 of a mile. We have Roman foot, 296 millimeters. We have Roman pace being 5 times of foot. We have Roman mile being 1,000 Roman pace. Notice again how NTTPs make this library easy to define things. Again, not possible before C++20. Also, specifying text before C++20 was really tricky. Right now, it is quite easy to use. Interpret parameters. However, it turns out that the Persian geographer was not using European Roman system, was using Arabic mile when he communicated his measurements. And the Arabic mile had different length than the Roman one. I also provided the currently measured with satellites and all of the current technology length of a mile of an equator. We can create here the lengths of Columbus degree, Afraganus degree, and equator real degree. We can define the function measuring an error. It takes approximate value, exact value. We just constrain it to find out if we can subtract them. We subtract, take absolute value, divide, and we have an error. I can put Roman mile, Arabic mile, both of them to the error, express them in meters, and we'll find out that the difference is quite significant between what Columbus assumed and what Afraganus stated. 31% difference already during calculation. Let's go further. So let's put this degree, multiply it by 360 degrees, and let's find the equator length by Columbus, Afraganus, and real equator length. If you print it out again, this time in nautical miles, we'll find out that Columbus' equator length was 16,000 nautical miles. Alfraganus claimed it is 23, and the real one is 21,000. So the truth was somewhere in between. So actually, it makes the error of Columbus a bit shorter, a bit smaller. So luckily for him, because Alfraganus overestimated the size of the Earth. But this was one of the errors during preparations for the travel. Second one was based on the apocalyptic book that is provided in some English versions of the Bible. This book, Two Estradas, says that 6 parts are habitable and the 7th is covered with water. If you're preparing for a life's adventure, for a travel, why not trust the Bible, right? If the land is 6 parts of the Earth, and the water is just the 1/7, then let's go. So Columbus estimated that the distance in degrees from Canaries to Japan or India is just 68 degrees of latitude, which is really optimistic if we know current geography. Because, well, how much water can be on the Earth, right? According to the Bible, it's not much. Tenerife Bahamas distance is 6,000 kilometers nearly. Tenerife Japan distance is 10,000 nautical miles. If I'll print all of them in the same unit, nautical miles, find out the error, we'll find out that Columbus' distance that he planned to travel was 3,000 nautical miles. The real distance to the target is more than 3 times longer. He made an enormous error during his estimations. And now he prepared all of the stocks, food, water, and went for the travel. He was so lucky that he found ground in the meantime, because otherwise we'll never hear about Columbus anymore. Because the real distance between Tenerife and Bahamas is just 3,200 nautical miles. So they just suffered without food for 200 miles. Of course, he probably had a bit more as a spare. So probably they were quite fine. But knowing this story, I know why he was so happy to get there and survive. All right? Notice that the code I provided to you was coded by construction, right? Thanks to the usage of the quantities and units library, we could focus on the business logic of our application, and probably no one of you had to track and do code review if I'm doing quantities right. And I use really different strange quantities like Roman miles, foot, feet, and Arabic miles, and nautical miles, meters, kilometers, everywhere. And this just worked. This was just self-explanatory, easy-to-use code, and we don't have to scope on this. We just have to scope on the logic of the program by itself. Imagine that you had to implement this with conversion macros. This would not be that fun and easy to follow during those slides, right? But those features are probably obvious to you. However, implementing a physical quantities and units library is much harder than it may initially appear. Plenty of people tried, because how hard can it be? And plenty of them stopped in the meantime, because it's much harder than it initially appears. There are, even talking about just safety, I'm not talking about correctness, about some other corner cases, there are other aspects that are not that obvious, and I would like to explain them in the following slides. For example, let's talk about duration that we have in the standard for more than 10 years. We are having here structure X that has a vector of chrono milliseconds. And we initialize it with mPlaceBack 42. Can you see some issues already? What will happen if tomorrow I will refactor this code to use microseconds? code continues to compile fine, but has largely incorrect values inside. This is not safe, right? This is something that we didn't think about it. We thought that duration is a really great type, and it is. It was revolutionary at the time it was standardized. No one thought about issues like this at this time. But it's inherently unsafe today, as we know, and there are plenty of issues already that happened because of it. With usage of quantity library, those issues are not a problem because this will never compile. In MP units library, it is not possible to create a quantity from just a value. You always have to spell a unit. If the unit doesn't match, it will either do the conversion or fail at compile time if it's truncating, as you've seen before, right? And you can use either multiply syntax or you can use two-argument constructor, depending how you like, what you prefer. But you always have to provide two entities rather than just one. Another issue is something that probably you realize, but it's also source of the issues, is that if you want to work with some legacy function that takes seconds, with pseudo duration, you have a function called count to return that, right? You have m plays back in 42 seconds, function takes seconds, so I'm fine taking count, right? Or not? Units match, right? Seconds, seconds, count. But the intermediate type you are storing it is microsecond. So the count on microseconds will not return you seconds, even if you put seconds inside. And this will be the result. Wrong by really huge magnitude difference. Of course, there is a tool called duration cast in the standard to force it, but you have to apply it and remember about it every single time. It turns out the users don't remember about it, don't want to care because today it works fine, the types match, but they may not match tomorrow, right? So it's not enforced by the design of the library. With MP units, we know it's more variables, but we want to be on the safe side. You always have to spell numerical value in and provide a unit. Even if it's the same unit you are using, you have to spell it. And it will always provide you correct value. If the conversion is needed, the conversion will happen. If it's not truncating, otherwise compile time error again. So in this case, you're putting seconds, it's converted to microseconds, and then 2 seconds back. And everything works fine. So numerical value getters in MP units always require a unit and an argument in order to provide type safety. Do you remember Clarence that has too small enclosure for him? Right? Let's try to build an enclosure for Clarence. We want to implement a box. This is how you do without the units library. Length, width, height. Length, width, height, all of them are doubles. You have area, multiplying length by width, return the double, works. Using any other library on the market, this is how you implement. Length, 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 area. Is it safer? Probably not, right? But this is the state of all of the libraries we have on the market right now. Nearly none of the libraries on the market try to solve it. And as Norman would tell you, that the discriminating between different lengths matter, right? You want to provide a vertical cage rather than horizontal one for this pet. So that's why we introduced a new abstraction called quantity spec, because dimension is not enough to specify all properties of a quantity. There may be more than one quantity for the same dimension. We may have the quantities of the different kinds, frequency, modulation rate, activity, still having the same dimension, or quantities of the same kind, even like length, width, altitude, distance, radius, position vector, wavelength, and more. Quantities may have different character, scalars, vectors, tensors. Some of them are also defined as non-negative, and you would like to express all of those and benefit from the safety introduced by those abstractions. ACCU specifies all of those quantities as quantities of length. And they form a tree, a hierarchy. There's plenty of those, and you want to benefit from such abstractions. User can also easily extend those trees with their own types. So let's add something like horizontal length. We're just stating that it is a quantity of length as a leaf of length. And you have horizontal area being a leaf of area with the equation being horizontal length times width. So it is a horizontal area. We may check that horizontal length is a length, but not every length is a horizontal length. Every horizontal area is an area, but not vice versa again. And then we can also convert length by length to area, but we cannot convert length by length to horizontal area because not every length by length is an horizontal area. But horizontal length times width always is an area, and horizontal length times width is horizontal area. So all of the logic works and provides additional type safety. So this is how you can implement this with MP units. You specify quantity of horizontal length, quantity of width, quantity of height, provide the constructor, and provide the floor being a horizontal area. It's up to the user to specify how the user wants to initialize it. Users may totally ignore the fact that we are using strong typed quantities and just provide those things, which is unsafe again, but easier. User may decide that they don't want to care. But if the user care, then you can provide either this syntax or this syntax, and this will create proper quantities of a strong type. There is a small difference of how it's done under the hood, but the resulting thing is exactly the same. So it's up to the user to define if they want to be safe or not in any of those things, but as a vendor, you may provide libraries that are always type safe. And user may decide either to opt into the safety or just use simplest thing if they don't care in this specific case. If you will reorder arguments, provide an error, you will get a nice error message saying that no non-conversion from quantity of height to a quantity of horizontal length. And this was our intent here. And then Norman will be happy. Another possible issue is, what should be the result of this calculation? 1 Hertz plus 1 becquerel plus 1 baud. Hertz is a unit of frequency, becquerel is a unit of activity, baud is a unit of modulation rate. All of them are quantities of dimension of time minus 1. I asked several different libraries in the market. Boost units that doesn't have baud, so I just use Hertz and becquerel, and claims it's 2 Hertz. I thought maybe it's always left-hand side, right? That's being taken. Let's try another one. What's the result? 2 Hertz again. I asked another library in the market, one of the most popular ones and a really good one. The answer was 2 seconds to minus 1, something a bit better because it's a common unit, right? But still, this addition was allowed. I asked Pint. Pint has baud. 3 Hertz. I tried again the reverse version. 3 becquerel. I asked Java what they do. Don't laugh. This is how people in Java have to do arithmetics. And I get an error. What do you think? Which one is correct out of those answers? Java. Java is correct. This should not compile. And actually, this compile time error is freaking good. It's really, really good one. And this is entire error. There is no 10 pages more, like in C++. This is runtime, but some things are detected in compile time as well. I actually think it could be compile time. I don't remember right now, but I have proper analysis in my other talk. Java has something found at compile time, some of them are found at runtime. Pint always finds in runtime. There is no way to find something at compile time because there is no compile time in Pint. But in Java, some things are found at compile time, and the results are really, really good one. I'm really happy to see those results. I mean the error messages. I hope that at some point in C++ we'll be able to have something similar, but we'll see. There is a paper proposal for C+26 that allows us to provide better text, better tracing of error messages. Hopefully it will be able to provide something similar. Why the Java is correct here is that ISO 80000 says that there is something called quantity kind, and says that quantity may be grouped together into categories of quantities that are mutually comparable. Mutually comparable quantities are called quantities of the same kind. Two or more quantities cannot be added or subtracted unless they belong to the same category of mutually comparable quantities. Quantities of the same kind with a given system of quantities have the same quantity dimension, but quantities of the same dimension are not necessarily of the same kind. Those are the official definitions from ISO 80000. And Java was the only one that was correct here. And if you look into the ACCU definitions, there are plenty of definitions of quantities of dimension t-1. Angular velocity, frequency, rotational frequency, angular frequency, activity, transfer rate, and many others. In order to express kinds specified here, we introduced kind of modifier. It denotes a family of quantities belonging to the same kind, to the same tree of quantities, like quantities of length that you've seen before. Can be obtained through getKind. If you call getKind of width, it will be the same as getKind of height. And getKind of width is actually kind of ISQ length. Kind of quantity spec is implicitly convertible to any quantity from its tree. So kind of ISQ length is implicitly convertible to, for example, width. So it behaves like any quantity from the tree. Quantities of the different kinds can't be compared, added, or subtracted. So if you provide definitions for base units in SI, we specified that each of those units is useful for specific kind only. This is only for kind of time, kind of length, kind of mass, and so on, right? So meter can be used for anything, width, height, radius. It expresses entire kind, entire tree. For the rest units, you may just provide the equation like here for Joule, or you may also say that some of them are restricted to specific kinds only, like radian, steradian, hertz, becquerel, have associated kinds that they operate only, right? Because hertz and becquerel are not the only ones that are interesting here. Radian, steradian also are the use cases, and you don't want to do addition on radians and steradians in the same equation, right? It means something totally different. So what is the result of this equation? In MP units, compile time error, invalid operands to binary expression. Most of the libraries on the market happily allow such operations and provide an incorrect result. So those things will compile in other libraries. Initialization of C-words to grace, for example, will compile. Some libraries, for example, AU, Aurora units, decided to not provide C-word, I think, or a gray, but one of those is not provided in SI at all because they are afraid of those errors. So they say it's better to not provide a unit at all rather than provide them and support convertibility. Also, this one will compile on every library on the market, including Pint and all of the C++ libraries, which is totally nonsense, right? What does it mean to add radian plus bit and compare this to steradian? But this compiles fine on most of the libraries on the market. So dimension is not enough to describe quantity, and that's why we provide quantity spec abstraction. Besides that, we have Affine spaces that we already discussed briefly before. In Affine spaces, we have points and displacement vectors, right? Points provide specific position, and displacement vector provides a difference between two different points. And we can do a limited set of operations in the affine space domain. With this, we can prevent some strange, some incorrect operations at compile time, if only possible, right? If I have two quantity points of temperature, I should not be allowed to add them. And this is found at compile time. Invalid affine space operations involved adding two quantity points, subtracting quantity point from a quantity, multiplying, dividing quantity point with scalar, multiplying, dividing quantity point with a quantity, multiplying, dividing quantity points with themselves, mixing quantity points of different quantity kinds, mixing quantity points of inconvertible quantities, and mixing quantity points of convertible quantities but unrelated origins. So let's look how it may be applied in practice. Let's go back to our Guardian article that provides incorrect article title for US market. This is how we defined Kelvin. Kelvin is first, before we define Kelvin, we have to provide point origin for the scale of Kelvin. We provide absolute zero for thermodynamic temperature. And then in Kelvin definition, besides the symbol and the kind, we specified also the origin. For Celsius, we provide another origin that in this case the origin is not absolute, so it's not like a beginning of the scale, it's relative. Relative because we say it's offset by this number of millikelvins from absolute zero. And then we provide this 0 degree Celsius to degree Celsius definition as well, not just a unit and a symbol. And also we have Fahrenheit, that has exactly the same. We're providing the origin for Fahrenheit, and we provide a unit of Fahrenheit, putting the origin into the unit. With all of this information in the type system, we can write quantity point being max temperature in degrees Celsius, average temperature in degrees Celsius, and provide the delta between those. If I print the title for EU market, I just print the delta. If I print the title for US, I take the delta in degree Fahrenheit, and I have correct temperatures being printed. And this works on a quantity because subtracting two quantity points is a quantity. If I want to print another part of this article, by Saturday, parts of Malawi saw a maximum temperature of compared with an average of nearly for the time of the year, I'm using points for this case. And in order to print the point, I have to take quantity from zero, because point by itself right now cannot be printed in the library, because point may mean different things and may be measured according to different reference things. So we don't provide automated support for printing that. We always have to take quantity from some point. So we take quantity from zero for max. And we do the same for max in degree Fahrenheit. And the same for average here. And we get information that this is 43 Celsius and this much of Fahrenheit, 25 Celsius, this much or Fahrenheit, but this time for points. This was for quantities. Different conversions, different calculations, easy to use, hard to abuse. Points are more common than most of us imagine. Points are everywhere around us, and typically we are not using them because we just don't have enough experience with them. We have temperature points, of course. We have timestamps because this is in chrono, so this is obvious choices to use points. But there are also others. Like if I stand on the mass every single day, reading my mass, this is a point. And those points can be subtracted, and I can find out what is delta mass, or the change of my weight between different days, right? Altitudes of the mountain peaks on the map. Current path length measured by car's odometer. Today's price of the instrument on the market. All of those are points. Improving the affine space points intuition will allow us to write better and safer software. Talking about points, let's see maybe another example. The Cochrane-Bricken bridge case that we discussed, right? As we said, German uses North Sea as a reference. It's so-called Amsterdam sea level. Swiss is using Mediterranean Sea. The difference is 27 centimeters. The main architect says that the difference of 27 centimeters was certainly known and everything had been drawn correctly on the paper. But something went wrong, right? Even during the early construction phase, it became clear that something was wrong. At Christmas 2003, the bridge builders received an unpleasant gift, a clear difference that was bigger than 27 centimeters. a sign error was hidden with the calculation of the responsible engineering office of the Swiss side. Instead of 27 centimeters higher, the Swiss built 27 centimeters lower, which doubled the difference to 54 centimeters. So let's see how we can implement this thing. You have Amsterdam sea level being absolute point origin. So it's like our ultimate zero on the scale. And we say Mediterranean sea level is a relative point origin relative to Amsterdam minus 27 centimeters. I can define types for quantity point of altitude in meters for Amsterdam and Mediterranean, being the German and Swiss altitudes. And then I just made it up. I don't know what's the height of the bridge, but let's assume this altitude is 330 meters. We provide some point, expected bridge altitude, right? The road level on the bridge. We look for both landmarks on both sides of the river. Let's assume 300 meters. There should be some landmark somewhere saying this is 300 meters measured by our scientists on both sides of the river. Then we find out where is the base of the ground to build the pillar, how much higher and lower it is compared to the landmark that we found. And we found out what is the altitude of the base of the bridge. Then we can find out what should be the pillar height, right? If you find the expected altitude of the road on the top of the bridge and the base of the pillar, we can find out what will be the height of each pillars. And then we can find out that the bridge pillar height on Germany and Switzerland, of course, those are made up values. I wasn't measuring this exactly there, right? Will be 27 meters, 32 meters. Road altitude will be 330 and 330 with 27 centimeters difference here. If you will measure this according to the same Amsterdam sea level, quantity from Amsterdam sea level, you will get exactly the same altitude. This is what you expect, right? So this is where the library helps us in many different places, and many of those things maybe they were not obvious for you in case you thought about doing this as a homegrown or in-house library in your company. Or if you did it already, you probably found issues like this, or maybe even other, on your journey by implementing that. But those libraries are not bulletproof. There are some potential issues that still may arise. Let's talk about them. What would you expect as a result of such division? If you divide 5 hours by 120 minutes, what would you like to see here? Let's keep the answer in our heads, and let's come back to this in a few seconds. Now let's see this solution. If I divide 100 kilometers per 2 hours, probably all of us will expect to see 60 kilometers per hour, right? This is obvious case. If this has to work this way, then this has to return 0. Because all of the units go to a type, and we just divide 5 by 24. If you write int equals 5 divided by 24, none of us will be surprised that the result is 0. In this case, it may be a bit surprising. In this case, maybe even more. But the library will not try to bring it to a common unit before division, because it will mean that we'll have to try to find a common unit here as well, or here. It has to be consistent. So dividing 5 hours by 120 minutes will be 0. This is why you should be aware that integer division is tricky. You should always prefer to work on floating point numbers with such libraries. By the way, modulo works okay. So if you do 5 hours modulo 120, it will be 1 hour difference. Another issue is that we lack safe numeric types in the library. And this goal of this library is not to implement those, right? We are doing whatever underlying representation type supports. If it's truncating, it is truncating. If it's undefined on overflow, it's undefined on overflow. You have to specify proper type in order to have safety in this domain, but we don't have those in the library, right? Integers can overflow. And there are already engineering issues like Ariane flight, V88, that crashed because of overflow on arithmetics. Integers can be truncated during assignment to a narrower type. Floating point types may lose precision during assignment to a narrower type as well. Conversions from 64 to double may lose precision as well. If you had such safe numeric types, our domain could be even safer. We would like to encourage anyone to come up with proposals if you have such types in your repositories. Please come out, provide papers, provide proposals, because we really need such types in the library for everyone to be safer. Also, having a type trait informing if a conversion between two types is truncating or not would help us to provide even better logic for this library as well. Right now we are doing as chronoduration does, but we know that it is probably not the best case, but we cannot do better unless we get this type trait in the standard library. Another question is, which style do you prefer, left side or right side? I got plenty of issues on GitHub saying that this doesn't compile. Why doesn't compile? What's broken in the library? Right? In theory, quantity is a number multiplied by a unit, by a reference, as all of the standard says. So in fact, this is correct. This is unit, this is number. But none of the users wanted to write this way. So we had to do some compromise. And we allowed this syntax. But this means that this also compiles. And what is the result of that? This is not speed. Right? If you will try quantity of speed, provide some strong type here, some check, you will get a compile time error saying that, well, it is unit that multiplies hour and kilometer. Because this is how it works. Arithmetic in C++, right? You have 60 kilometers divided by 2 and then multiplied by hour. The correct solution is to put it in parentheses, of course. Then everything works fine. In order to support this syntax, we had to agree on this syntax, which is some trade-off. Also, if you have a function template, make length, you multiply raw value by meter and provide 42, everything looks nice. If I will provide 42 meters to make length, I will not get length anymore, right? This will be an area. However, fortunately, all of those errors can be easily found at compile time sooner or later in our application. Right? Initially, we produce errors for those cases, but in order to support this case, right now it's allowed and does it work. But as I said, we can find them easily at compile time sooner or later, because sooner or later you have to assign the result to some specific type. If you specify the result of this to a type or a strong or a typed quantity or a concept, you will get a compile time error. If you have this function make length, again, if you assign this to typed thing, you will get an error. If you will provide concept as a result of make length, you will have an error as well. If you specify there should be just a representation, not a quantity, again, you will get an error. So it's not that bad as it may seem, but there may be some potential surprises with this syntax. This is engineering trade-off, and we'll have to decide during the standardization process if you want to come back to this parentheses all the time, which is inconvenient on everyday basis, or agree to such issues that will be found later on, possibly a few lines later in our calculations. Another possible issue is that the library sometimes may allow irrational quantity combinations. Everyone probably can imagine length by length being an area, or width by height being an area. This is logical, right? But what does it mean? Height rather height times height being an area. It's hard to reason about this, but the library doesn't know the context. It's just length by length, it's an area, and it works. Right? We cannot constrain it to not work. So some combinations here may be illogical, but will work. Last but not least, Structural types. Quantity-to-quantity points class templates are structural types to allow them to be passed as template arguments. You've seen an example, for example, in our Hockenbrickel bridge example, when we passed 27 centimeters to a template defining relative point origin of Mediterranean sea level. This is a quantity passed to a template, so it has to be a structural type. Structural type has this nasty property that it has to provide all of the members being public, which means that all of the type safety we provide with all of those type safety getters that you have to always to spell the unit can be worked around by just getting the value directly from the type. And this is actually what I found out in my user's code, because from time to time I like to open Google and find out who is using my library and how, to find out how I can address the issues and how I can improve my library for the user's code to be better. And that's what I found. And I even provided a code review to this guy saying, well, this is not what you should do. Because initially we had number. Number was short, but it was unsafe because it didn't get unit. So you've seen that we renamed a number, we renamed it to numerical value in and required a unit. So it was a really long one. So the person found out I can do it shorter, because getting a value was shorter than calling my interface with a long name. We are lazy, right? And I provided a feedback. Please don't use members data directly. This is implementation detail and should not be used directly here. It seems I have to obfuscate the name more to discourage people from using it. The person agreed, but says, don't know if obfuscation would be effective. Maybe a shortened oxygen comment that discouraged the usage. Such a comment would pop up in most IDEs. So what I did, right after that code review, I changed the name of my member value inside of a structural type. I could provide a different name, but I wanted to be politically correct here. So I just spelled numerical value is implementation detail and provided a oxygen comment. Now it's longer than my ID, than my API for a getter, and hopefully no one will use it directly, but it's still provided as a public one. Hopefully at some point the structural type requirements will be loosened and in the standard, and then I will be able to put it in a private section of the class. But for now, it sucks that it has to be public. Question? No. Comment. Microphone. Yeah. Yeah. Comment.
Oh, sorry. Yeah. Most IDEs will also pop up all the public members when you type dot anyway, so you don't have to type it. You just select it from the list.
Yeah, exactly. So most IDEs just pop out the public members, and actually this is how I learned that this person found this member, because it was not through code review of my library implementation. This person just typed dot in the IDE, and this was the first thing that happened, the public member on the list. So it was just to be used, right? And this is actually how users will try to use it. The same happens, for example, for std_array. Std_array is an aggregate, so it has the member data public. But none of us probably never tried to use the data member in a standard library implementation publicly of std_array. But to summarize, because we are nearly out of time, MP units is, first of all, about safety, right? We have automated but safe unit conversions. We prevent truncation of data. As we've learned, explicit is not explicit enough in the C++ language. We have safe quantity numerical value getters. We can model quantities of the same dimension, but different kinds. We may provide various quantities of the same kind as well, and the affine space abstractions. Besides safety, you have plenty of more features in the library, so you're welcome to try it and provide feedback. Do you have any questions?